All right. In this video, I want to take a look at how we can progress from sending numbers over a wire to actually sending text from one computer to another. So let's think about um, early on. We said when we have two computers and there's a shared wire between them, um, that this wire can go into two states, and the states could be something like, off and on. It could be low voltage and high voltage. It could be positive voltage and negative voltage. Really doesn't matter. We just have to understand that, the voltage can be, the wire can only be in one of two states at a time. And this is because just setting a wire to one state or another is easy to do, and reading a wire and determining which state it is in is an easy thing for a computer to do. And generally, these are what the electrons are doing. But when we want to represent the two states of the wire, right, we talk about the states as zeros or ones. So once we start thinking about those states as zeros and ones, it becomes fairly obvious how you might send somebody a number, right? Well, what we'll do is one computer will just set the wire into a sequence of states, and another computer, while the wire is being set 0, 0, 0, 1, 0, 1, 0, 1, another computer is read, 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 and as long as they have their clocks synchronized, then the receiving computer should get the exact same set of states that the setting computer did. And so in this case, if the two computers had agreed that we are going to communicate on an 8-bit protocol where I'm going to interpret every 8 bits as a number, and this set of states comes across the wire, then the receiving computer might turn that into a 21. All right, that would just be the binary equivalent of this. So sending numbers is, I think, fairly intuitive. But let's think about if we wanted to send letters instead. All right. I think an obvious solution is we just have to develop some kind of mapping of numbers to characters on the keyboard. So, here's your standard keyboard. And if I were to go through my keyboard just pressing one time, holding or just pressing every button on it, and another time go through it again, only this time hold shift while I'm pressing every button, what I'm going to find out is that I have 95 typable characters. All right. And so I'm trying to develop an efficient mapping of characters to numbers that can be represented in binary. So what I'm wondering is, for this 95, is how many bits do I need? So I start thinking through, and I go, well, let's see. If I had 1 bit, I could represent 2 things. And 2 bits could represent 4 things. 3 bits can represent 8 things. And 4 bits is 16 things. You can see I'm just doubling here. 5 can represent 32. 6 can represent 64. And 7 can represent 128. Okay, so what I can see here now is that if I want to represent all 95 typable characters, and 95 falls between here and here, I need to use a 7-bit system, and that'll give me room to come up with a binary representation of all 95 characters, and some leftover room for maybe some other things we want to include in that character set, and you'll see that in a sec. So that's exactly what has been invented. Okay, so I've got here an ASCII reference sheet, and on this ASCII, it stands for American Standard Code for Information Interchange. This was invented in the 60s. And basically the reason for this is if you had different computers made by different manufacturers, that you'd still want them to be able to exchange information. So you couldn't have one company decided that the letter A was going to get mapped to this number, and another company mapping letter A to a different number, because then they would be able to communicate with each other. So what this does, as you go through it, these are the typable characters, and character 32 is the space character, and I can see these are the bits. So if I wanted to send the space to somebody, I would set the wire to 001 00000, and that would be the space character. And you can see over here, like from 65 down to 90, that's where the capital letters are. 97 to, let's see, to 122 are the lowercase letters. Then you got over here at the beginning some of your like punctuation marks and math symbols. And actually, right here, you can see that even if you want to send numbers, we have you would send the character for the number rather than the number itself. So like the character, the symbol 0 is actually going to be sent as this sequence of bits that represents 48. Okay, so this is ASCII. One more thing you may notice on here is that ASCII characters, I said just a second ago you only needed 7 bits, and 7 bits would give me from the numbers from 0 to 127. And then on here, all of these are 8-bit numbers, and you can see every single one on this table has a leading 0. Okay, so they're all padded to be 8 bits. And that's just because the byte, which is a chunk of 8 bits, became standardized, mostly for the reason that when you're doing stuff with software and hardware design on computers, things just work out easier if you, as often as possible, are dealing with chunks of information that are in powers of 2. All right, so 7 it's not a power of 2, so things maybe don't work out as well mathematically all the time. All right. One more little side note of this, but this is not really going to be related to sending text, but you'll notice that the characters all start at 32 and they go to 126. So I said we could go from 0 to 127. So we've got some extra space at the beginning and then the 127 at the end. The stuff before 32 is like control codes and characters you can't really see. So like backspace characters, delete characters, the tab character. And there's also some printer control characters in there. Like it's actually a character that says to tell the printer to turn the wheel and advance to the next line. So line feed characters, that kind of stuff. So the ones outside of this 32 to 126 are just codes that you might need to include in information, but aren't like characters that are actually on the keyboard itself. All right. So what might a message look like? All right. So suppose I had a message and I did 0, 1, 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, and 0, 1, 1, 0, 1, 1, 0, 0. And I guess I got to go to the next line. This is one long string of bits, but one, let's have a little more room. One, I lost my place. Let's do a 0, 1, 1, 0, 1, 1, 0, 0, and 0, 1, 1, 0, 1, 2, 3. 4 more ones. All right. So let's say I get this message. All right. So I'm reading the wire and it gets set to bits in this sequence. What I'm going to do as a receiving computer is I'm going to break this up into chunks of 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then here. And I can turn these into their decimal equivalents just for ease of finding it on the charts. So this would be 72. And this would be, let's see, this is 101, and this is 108, and this is 108, and this is 111. And if I went over to my table, all right, and the very first one I said was 72, and I go down there, it's 72, and that's the sequence of bits that goes with the capital letter H. So this is an H. And I go down here, and if I go back to the chart, 101, you'll see it's paired up with the lowercase e, and 108 is the L, and then this last one, let's see, 111, this will be an O. So if you wanted to send the message hello on a wire, this is what actually happens. The wire will get set to the two states in this sequence. And anyway, that's how ASCII works.